Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with Mercury's ghostly exosphere, the planet that shouldn't have air. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. The surface of Mercury presents a stark landscape marked by craters and vast plains formed from ancient volcanic activity. This region reveals a history of intense bombardment, resulting in a surface that appears both desolate and captivating. The proximity to the sun generates extreme temperature fluctuations, with daytime highs soaring to approximately 450 degrees Celsius and nighttime lows plunging to around -200 degrees Celsius. Such extremes influence its thin atmosphere, which is largely composed of oxygen, sodium, hydrogen, and potassium. The lack of a substantial atmosphere contributes to the absence of weather patterns typically observed on other planets. Ultraviolet radiation from the sun interacts with surface materials, leading to a delicate balance of erosion and renewal. The exosphere, while tenuous, is a critical aspect of Mercury's identity, allowing for the presence of transient particles that drift silently above the surface. Mercury's core is disproportionately large compared to its overall size, accounting for about 70% of its volume. This metallic core contributes to the planet's magnetic field, albeit weak, which is unusual for such a small body. Such features provide insight into the planet's formation and the dynamics that govern its evolution. This remarkable world, with its unique characteristics, challenges long-held assumptions about planetary atmospheres and their interactions with solar forces. An exosphere represents the outermost layer of a planetary atmosphere, characterized by an extremely low density of particles. These regions are tenuous, existing at the threshold where atmospheric particles begin to transition into space. This particular environment is often dominated by the influence of solar radiation and magnetic fields, which can strip away or replenish gases. The defining characteristic of an exosphere is its gradient, where particle density diminishes sharply with altitude. In the case of Mercury, this layer is composed primarily of oxygen, sodium, hydrogen, and helium, remnants of solar wind interactions and surface interactions. The absence of a substantial gravitational pull means that particles escape into space with relative ease, resulting in a fleeting collection of gases sustained by continual replenishment. Temperature fluctuations in this region are extreme. During the day, surface temperatures can soar to over 400 degrees Celsius, while nighttime temperatures plunge to nearly -200 degrees. Such variations profoundly affect the behavior of the exosphere, contributing to its transient nature. The dynamics of an exosphere involve constant interactions with solar wind, where high-energy particles collide with atmospheric constituents. As a result, this delicate balance shapes the chemical composition and distribution of the gases, creating a unique and ephemeral environment around the planet. Historical observations of Mercury reveal a complex relationship between humanity and this enigmatic planet. Early astronomers, limited by the technology of their time, regarded it with a mixture of curiosity and frustration. Due to its rapid orbit around the Sun, Mercury often appeared elusive, rising and setting in the sky with little warning. This fleeting visibility contributed to its reputation as a harbinger of change, influencing ancient cultures and mythologies. The first telescopic observations in the 17th century significantly enhanced understanding. Notable figures such as Galileo Galilei, documented the planet's phases similar to those of Venus, providing evidence of its spherical nature. This revelation was pivotal, aligning with the emerging heliocentric model of the solar system. In the 19th century, advances in observational techniques allowed for more detailed studies. The discovery of Mercury's surface features, though initially vague, suggested a rugged terrain shaped by geological forces. The planet's proximity to the Sun hampered further exploration, leaving many questions unanswered. With the advent of space exploration in the 20th century, the Mariner 10 mission in 1974 marked a turning point. High-resolution images revealed a cratered landscape, strikingly reminiscent of the Moon. These findings sparked renewed interest in its atmospheric phenomena, revealing the unexpected presence of a tenuous exosphere, a ghostly feature defying prior assumptions about planetary atmospheres. Studying atmospheric phenomena plays a critical role in understanding planetary science. Investigations into exospheres, such as Mercury's, provide insight into the processes that shape celestial bodies. The examination of these elusive layers reveals information about surface interactions, volatile materials, and space weather influences. This region's atmosphere, although extremely thin, is a crucial element in piecing together the planetary puzzle. Analyzing how it evolves over time allows researchers to grasp the dynamics of energy exchange between solar radiation and the planetary surface. Understanding these mechanisms helps clarify how atmospheres develop and dissipate, shedding light on the conditions necessary for atmospheric retention. The impact of exospheric studies extends beyond individual planets. They offer comparative data essential for understanding atmospheres across the solar system and beyond. These observations assist in the exploration of planetary habitability, illustrating how different bodies respond to their environments. Insights gained from Mercury contribute to broader theories regarding atmospheric phenomena on terrestrial planets, including Earth itself. The importance of these studies is underscored by their implications for future exploration. Knowledge of atmospheric conditions informs mission planning, aiding in the selection of landing sites and scientific objectives. It shapes our understanding of planetary evolution and the potential for life, ensuring that every exploration mission builds upon the foundation laid by atmospheric research. The exosphere of Mercury, an ephemeral layer of gases, presents a fascinating chemical profile, composed primarily of oxygen, sodium, hydrogen, helium, and potassium. This thin veil of particles offers insights into the planet's unique environmental conditions. The abundance of oxygen, though surprising given its proximity to the Sun, derives from solar radiation and the sublimation of surface materials. Sodium, often detected in higher concentrations, contributes to the exosphere's dynamic nature. Its presence is linked to the planet's geological processes and interactions with solar wind. Potassium, albeit in smaller quantities, adds complexity to this atmospheric composition. These elements, influenced by solar activity, undergo continuous variation, reflecting the delicate balance between external forces and surface characteristics. The identification of hydrogen and helium further emphasizes the exosphere's tenuous existence. These light gases escape easily into space, resulting in a constantly replenished atmosphere that is more akin to a fleeting whisper than a traditional air envelope. This chemical analysis not only illuminates the planet's surface processes, but also hints at interactions with the solar environment. By understanding these components, researchers can infer the historical and ongoing influences that shape Mercury's exosphere, revealing the intricate connections between a planet's geology and its atmospheric phenomena. Outgassing plays a crucial role in the formation of Mercury's exosphere. This process involves the release of volatile substances trapped within the planet's surface. When temperatures reach extreme highs, materials such as sodium, potassium, and magnesium escape into the thin atmosphere. This release results in a transient yet dynamic exosphere, with constituents fluctuating based on the planet's thermal cycles. The extreme temperatures, which can soar to over 400 degrees Celsius during the day, facilitate this outgassing phenomenon. Solar wind, a continuous stream of charged particles emitted by the sun, contributes significantly to the exosphere's composition. As these particles collide with Mercury's surface, they displace atoms and molecules, further enriching the exosphere. The interaction between solar wind and the planet's magnetic field generates a complex interplay, resulting in the ionization of some exospheric elements. This process allows for the formation of ions that can escape the planet's weak gravitational pull, adding to the elusive nature of Mercury's atmosphere. The delicate balance between outgassing and the influence of solar wind illustrates the ongoing evolution of this planet's exosphere. Each of these factors contributes to a fragile layer that defies the expectations of a planet so close to the Sun, showcasing the complexities of planetary atmospheres even in the harshest environments. Solar radiation plays a pivotal role in the formation and maintenance of this tenuous exosphere. Intense solar wind, a continuous stream of charged particles emitted by the Sun, interacts with Mercury's surface. This interaction facilitates the release of atoms and molecules, which momentarily escape the planet's gravitational pull. Elements such as sodium, potassium, and calcium, originating from the surface, become part of this ephemeral atmosphere. The high-energy photons from solar radiation also contribute significantly. They can energize surface materials, causing them to vaporize and enter the exosphere. The faint glow of sodium, in particular, can be observed as a result of these energetic processes. This layer, while transient, is crucial in understanding the dynamics of Mercury's environment. Conditioned by its proximity to the Sun, the exosphere experiences continuous replenishment, yet it is also subject to erosion. The same solar wind that facilitates its formation can strip away these gaseous constituents. The balance of these opposing forces results in a delicate equilibrium where the exosphere is neither fully sustained nor completely depleted. Variations in solar activity further complicate this equilibrium. During periods of heightened solar output, the exosphere may swell, while quieter phases can lead to significant reductions. These fluctuations elucidate the intricate interplay between solar mechanisms and the atmospheric remnants of this planet. The unique orbital mechanics of Mercury dictate its relationship with the Sun, resulting in a peculiar cycle of day and night. This planet possesses an eccentric orbit, causing it to travel in a highly elliptical path. The varying distance from the Sun impacts solar radiation intensity, which in turn influences the atmospheric dynamics. As it approaches the Sun, temperatures soar, leading to the release of volatile elements from the surface, contributing to the delicate exosphere. The axial tilt, or lack thereof, further complicates its atmospheric conditions. With minimal tilt, Mercury experiences extreme temperature fluctuations between day and night, reaching highs of approximately 400 degrees Celsius during daylight and plunging to nearly -200 degrees Celsius in the dark. This harsh thermal environment affects the retention of gases, causing those in the exosphere to escape into the vastness of space. The gravitational pull from the Sun also plays a critical role in shaping this planet's atmosphere as it orbits. Solar wind interacts with the exosphere, constantly stripping away particles. This relentless process illustrates the delicate balance between the solar forces and the remnants of an atmosphere that should not exist under conventional expectations. The interplay of these factors creates a unique character, showcasing the paradox of a planet struggling to maintain its ephemeral air. The solar wind, a continuous stream of charged particles emitted by the Sun, engages with Mercury's magnetic field in a complex manner. This interaction is noteworthy due to the planet's weak magnetic shield, which is only about 1% as strong as that of Earth. The magnetic field, albeit diminished, plays a pivotal role in shaping the environment around this innermost planet. Charged particles from the solar wind collide with the magnetic field lines, creating a boundary layer known as the magnetopause. This region acts as a fragile barrier, preventing some of the solar wind from directly impacting the surface. These interactions result in a dynamic process, where particles are gradually trapped and funneled along the field lines. The solar wind can strip away lighter elements from the exosphere, constantly reshaping it. The tenuous atmosphere, primarily composed of oxygen, sodium, and potassium, remains in a delicate balance as the solar wind selectively erodes its constituents. This ongoing exchange between the solar wind and Mercury's magnetic field not only influences the planet's atmospheric composition, but also affects surface features, contributing to the ongoing degradation of its geological landscape. The consequences of these interactions reveal a planet that remains in a constant state of flux, embodying the tenuous nature of its existence within the solar system. Temperatures on Mercury fluctuate dramatically between day and night, a consequence of its slow rotation and proximity to the Sun. During the day, surface temperatures can soar to approximately 427 degrees Celsius. This intense heat results from direct solar radiation, with little atmosphere to mitigate its effects. The landscape transforms under these conditions, causing materials to expand and warp, while the surface becomes a scorched terrain, devoid of any moisture. In stark contrast, nightfall brings a sharp decline in temperature, plummeting to near -173 degrees Celsius. The absence of an insulating atmosphere allows heat to escape rapidly, leading to these extreme nocturnal conditions. The cold darkens the landscape, casting shadows that stretch across the bleak surface, revealing a stark and desolate beauty. These temperature extremes influence the geological processes occurring on Mercury. Thermal cycling contributes to the gradual breaking down of rocky materials, as repeated expansion and contraction create fractures and fissures. The interplay between intense heat and frigid cold shapes the planet's surface features, including its vast plains and craters. Such dynamics illustrate the duality of existence in this region, where scorching sunlight and frigid darkness coexist, defining Mercury's identity and highlighting the complexities of its environmental conditions. Temporal and spatial changes within Mercury's exosphere reveal the intricate balance between solar influence and the planet's own geological characteristics. This tenuous layer, composed mainly of oxygen, sodium, hydrogen, helium, and potassium, experiences significant fluctuations. These variations are primarily driven by solar radiation and solar wind interactions, which operate on a cycle dictated by the planet's swift orbit around the Sun. During periods of heightened solar activity, the exosphere expands, as particles are ejected from the surface and driven into the upper atmosphere by energetic solar particles. Such events result in increased density and temperature, altering the chemical composition of this fragile envelope. Conversely, when solar activity diminishes, the exosphere contracts. This dynamic behavior signifies a delicate equilibrium, reflecting the planet's inability to retain a stable atmosphere. Spatially, distinct regions display different characteristics. Areas near the equator often show greater particle density due to the direct impact of sunlight, while polar regions exhibit a more tenuous presence. This discrepancy is influenced by the planet's axial tilt, which remains nearly non-existent. Consequently, sunlight bathes the equator more consistently, allowing for a richer interaction between solar particles and surface materials. These shifting patterns underscore the complexity of Mercury's exosphere, emphasizing the interplay between solar forces and the planet's unique physical attributes. The constant bombardment by micrometeorites contributes significantly to the dynamics of Mercury's tenuous atmosphere. These small, high-velocity particles strike the surface with enough energy to dislodge atoms from the exosphere. Each impact creates a series of tiny craters, serving as a testament to the planet's relentless exposure to space debris. This region, with its scarce atmosphere, allows for an efficient transfer of energy, leading to the vaporization of surface materials. The phenomena associated with these impacts result in a gradual loss of atmospheric constituents. Lighter elements, primarily sodium and potassium, are particularly susceptible to being propelled into space. The relentless nature of this process creates a delicate balance, where the incoming particles continuously erode the already thin exosphere. This erosion highlights the fragility of the atmospheric layer, which is perpetually replenished by the surface, but never fully stabilized. Additionally, the velocity of micrometeorites is often sufficient to overcome Mercury's weak gravitational pull. Consequently, once elements are released from the surface, they can escape into the vacuum of space. This ongoing cycle of impact and loss underscores the unique environmental conditions of Mercury, revealing the planet's vulnerability despite its proximity to the Sun. The intricate relationship between these impacts and the atmospheric composition provides deeper insights into the intricacies of planetary atmospheres within our solar system. This region's exosphere is strikingly tenuous, a mere whisper of atmospheric presence compared to other planetary bodies. Mercury's exosphere possesses a density that is several orders of magnitude lower than that of more substantial atmospheres, such as those found on Earth or Venus. The sparse collection of atoms and molecules is continually replenished primarily by solar-wind interactions and the disintegration of surface materials through micrometeoroid impacts, contrasting with the thick, nitrogen-rich atmosphere enveloping Earth. The constituents of Mercury's exosphere consist predominantly of oxygen, sodium, hydrogen, and helium. Their fleeting existence is a testament to the planet's proximity to the Sun, where intense solar radiation facilitates rapid escape velocities. This ephemeral nature results in a situation where the exosphere is not only thin but constantly in a state of flux. Mars, while also possessing a thin atmosphere, offers a denser alternative compared to Mercury. Carbon dioxide dominates its gaseous envelope, allowing for a more stable atmospheric presence. The comparative examination reveals a spectrum of atmospheric retention capabilities, influenced by gravitational forces and solar interactions. In this context, Mercury stands as an exceptional case, a planet with an atmosphere that defies expectations and challenges our understanding of planetary formation and evolution. Volatile elements play a pivotal role in the composition of this planet's tenuous exosphere. Sodium and potassium, both highly reactive and essential to understanding Mercury's atmospheric dynamics, are present in unexpectedly high concentrations. They contribute to the unique characteristics of the exosphere, influencing its behavior and interactions with solar radiation. Sodium, in particular, manifests as a faint glow, detectable during specific conditions. This element is continuously replenished, drawn from the surface through processes such as sputtering, where solar wind particles collide with the regolith. The ongoing influx creates a dynamic equilibrium, allowing sodium to persist despite the planet's harsh conditions. Potassium, while less abundant, exhibits similar volatile properties. Its presence hints at the geological processes that shaped Mercury's surface. Together, these elements reveal a complex interplay between solar activity and planetary geology. The exosphere, while lacking the density typical of larger planets, showcases the ability of these light elements to exist in a thin envelope, almost ghost-like. They serve as markers of the ongoing interactions between Mercury and its environment, illustrating the balance between loss and replenishment. Such insights into these volatile elements deepen our understanding of how this planet maintains its ephemeral atmosphere against overwhelming odds. The discovery of water ice at Mercury's poles introduces a profound layer of complexity to exospheric studies. This finding suggests that despite the planet's extreme proximity to the Sun, it harbors stable water in shadowed regions where sunlight does not penetrate. These icy deposits, existing in the cold traps of craters, form a stark contrast to the planet's otherwise scorching surface temperatures, revealing a delicate balance of thermal dynamics. The implications extend beyond mere presence. The existence of water ice indicates potential for localized moisture within the thin exosphere, influencing its overall composition. The interaction between these ice deposits and the solar wind may facilitate processes that contribute to the exosphere's maintenance, possibly through sublimation and subsequent redistribution of water vapor. Research shows that this vapor can interact with the surface and the solar wind, forming a transient layer that could affect the planet's atmospheric escape mechanisms. Understanding how this water interacts with the surrounding environment offers insights into the stability and evolution of Mercury's atmosphere over geological timescales. This phenomenon raises questions about the origins of the ice itself, prompting investigations into whether it originated from cometary impacts or was produced in situ. Each new discovery adds a layer of depth to the broader narrative of planetary atmospheres within our solar system. The Messenger mission provided crucial insights into Mercury's enigmatic exosphere. Launched in 2004 as it embarked on a journey to unveil the secrets of this planet, often referred to as the innermost world. As it approached, advanced instruments began to gather data, revealing an atmosphere that is tenuous, composed primarily of oxygen, sodium, hydrogen, and potassium. This investigation illustrated the complexities of exosphere formation under extreme solar conditions. The spacecraft's measurements indicated that the exosphere is not stable. It experiences constant fluctuations influenced by solar wind interactions. These dynamic shifts underscore the delicate balance between solar energy and the planet's weak gravitational pull. Observations captured the transient nature of this thin layer, showcasing how particles can escape into space, only to be replenished through ongoing geological activity and solar interactions. Surface features, such as the numerous impact craters and volcanic plains, played a significant role in the composition of the exosphere. Data collected revealed how these geological processes contribute to the release of gases, further enriching the thin atmosphere. Messenger's findings established a baseline understanding of Mercury's exosphere, guiding future studies. This mission effectively transformed our understanding of planetary atmospheres, illustrating the unique conditions that result in the existence of such an ephemeral layer around a seemingly inhospitable world. Measurements of exospheric density present a range of methodologies and challenges unique to this planet. Instruments designed to capture the faint traces of particles rely on precise calibration and sensitive technology, given the tenuous nature of Mercury's atmosphere. The exosphere consists primarily of oxygen, sodium, hydrogen, and some heavier elements, existing in such low densities that the instruments must detect individual atoms. Vasi doelva mediu gaidenio twen at the end. The challenges arise from the proximity of the Sun, which exerts a significant influence on the exosphere. Solar winds and radiation bombard this region, inducing the release of atoms from the surface and creating transient spikes in density. This variability complicates consistent measurements. The need for real-time data collection becomes apparent, as the dynamics of solar interaction can change within seconds. Instruments like mass spectrometers and particle detectors aboard spacecraft have been crucial in capturing this data. They operate by analyzing the composition and velocity of particles, allowing scientists to infer density profiles. Each measurement must be interpreted with caution, accounting for both the planet's gravitational pull and the solar influences. The delicate balance of forces at play creates a complex system that challenges our understanding of atmospheric retention in extreme environments. Insights gleaned from these methodologies continue to expand knowledge of planetary atmospheres across the solar system. Extreme temperatures on Mercury significantly influence the composition of its ghostly exosphere, with surface temperatures soaring to approximately 450 degrees Celsius during the day. This region is subjected to conditions that strip away atmospheric constituents. The intense solar radiation causes volatile elements to vaporize, creating a tenuous layer of atoms and molecules. This exosphere consists primarily of sodium, potassium, and calcium, elements that are otherwise rare in more stable atmospheres. Their presence suggests a complex interplay of solar wind interactions and surface material evaporation. During the night, temperatures plummet to around -170 degrees Celsius, allowing some of these particles to condense and settle onto the surface, altering the chemical landscape. The lack of a substantial gravitational field further complicates the retention of these elements, leading to a continuous cycle of loss and replenishment. Solar wind constantly bombards this region, contributing to the exosphere's dynamic nature. The particles can be ejected into space, while others may collide and interact, forming transient structures that fade almost as quickly as they appear. This delicate balance of temperature extremes and elemental behavior presents a unique case study in planetary science. Understanding these mechanisms provides deeper insights into the nature of exospheres beyond Mercury, contributing to broader discussions in astrophysics. Guramanstan ankering son nature's pozordig contributing to broader discussions in astrophysics. Guraman Kuda the T-mondial mechanis exosphere reveal a complex interplay of elements and molecules, predominantly composed of oxygen, sodium, hydrogen, and potassium. These constituents undergo various reactions influenced by solar radiation and the planet's extreme temperature fluctuations. Ultraviolet light from the sun plays a critical role in this environment, facilitating the breakup of molecules and enabling the formation of transient species. Photodissociation, in particular, breaks down oxygen molecules into individual atoms, which can subsequently react with sodium and potassium. This activity leads to the creation of a variety of compounds, albeit fleetingly, as they dissolve back into the vast emptiness surrounding the planet. These reactions are essential in maintaining the delicate balance of the exosphere, contributing to its ephemeral nature. Mercury's proximity to the Sun enhances the intensity of solar-wind interactions, further complicating the chemical landscape. Charged particles collide with the exosphere, potentially energizing atoms and altering their states. Some reactions result in the emission of light, a phenomenon that scientists study to glean more information about the composition and behavior of the exosphere. These terrene basemapheric layers are continually refreshed, with elements escaping into space while new ones are drawn in. This constant cycle highlights the dynamic yet fragile existence of this ghostly envelope surrounding the planet, providing crucial insights into exospheric processes across the solar system. The existence of this exosphere raises intriguing questions regarding astrobiological potential. Even in its tenuous state, it serves as a window into the fundamental processes that govern atmospheric evolution, revealing how celestial bodies interact with their environments. The composition of this thin layer, primarily consisting of oxygen, sodium, hydrogen, and other trace elements, suggests that even extreme environments can support complex chemical interactions. Research indicates that these constituents may play a role in various photochemical reactions, hinting at possibilities for organic chemistry to occur under the right conditions. The planet's proximity to the Sun, coupled with its extreme temperature fluctuations, allows for a unique interplay of energy that may drive such reactions. This aspect makes it an intriguing candidate for studying the limits of habitability, especially in the context of rocky planets. Although Mercury is not considered a likely host for life, the exosphere provides essential data on how atmospheres can arise and evolve. Understanding these processes could inform the search for life on other celestial bodies, particularly those with similar harsh environments. The resilience of this exosphere serves as a reminder that even the most inhospitable locations can yield insights relevant to astrobiology, broadening our comprehension of life's potential across the cosmos. Interactions between the exosphere and surface geology reveal a complex relationship that shapes Mercury's unique environment. This tenuous layer of gases is influenced by the planet's extreme temperature fluctuations, which can swing from approximately -170 degrees Celsius at night to over 400 degrees Celsius during the day. Such variations contribute to continuous processes of erosion and deposition on the surface, where solar winds and micrometeorite impacts play a pivotal role. The surface, marked by vast plains and rugged cliffs, exhibited evidence of volcanic activity and tectonic movements. These geological features provide insight into the planet's thermal history and its ongoing evolution. Volcanic outgassing may have contributed to the formation of the exosphere, releasing elements like sodium and potassium, which are now part of this delicate atmospheric layer. In addition, the constant bombardment by solar radiation and micrometeoroids leads to the gradual release of particles from the surface, further enriching the exosphere. Dust and other particulate matter are lofted into this region where they can interact with solar winds, causing transient phenomena that are of keen interest to scientists. Analyzing these interactions assists in understanding not only Mercury's geology, but also the broader implications for planetary atmospheres within the solar system. The contrast between Mercury's exosphere and that of the Moon reveals intriguing insights into their evolutionary processes. Mercury, despite its proximity to the Sun, maintains a tenuous atmosphere that is constantly replenished by solar wind and micrometeorite impacts. This region, characterized by its fluctuating composition, exhibits trace elements including sodium, potassium, and oxygen, which are continuously lost to space. The dynamic nature of this exosphere suggests ongoing geological activities beneath its surface, hinting at a complex interplay of solar forces and planetary characteristics. And the stark contrast, the Moon possesses an exosphere that is even more fragile and lacks the richness found on Mercury. This environment comprises a minimal collection of exhalations from its surface, including helium, neon, and hydrogen, which are not sustained by any active geological processes. The absence of significant atmosphere results in a stark, barren landscape where solar radiation directly impacts the regolith. Studying these two celestial bodies allows researchers to explore the effects of gravity, solar radiation, and magnetic fields on atmospheric retention. The stark differences in their exospheres highlight how varying conditions can lead to diverse atmospheric phenomena. Despite their similarities in size and proximity to the Sun, understanding these variations aids in refining models of planetary atmospheres throughout the solar system. Gravitational forces play a crucial role in maintaining the tenuous stability of Mercury's exosphere, despite its proximity to the Sun, which generates substantial energy input. The planet's weak gravity limits the retention of atmospheric particles. This region, characterized by an extremely thin atmosphere, contains atoms and molecules that are continuously bombarded by solar radiation. The intensity of this radiation contributes to the escape of lighter elements, such as hydrogen and helium, which are unable to be held by the planet's gravitational pull. Interactions between solar wind and the exosphere create a dynamic environment where particles are constantly lost and replenished. The balance between gravitational attraction and solar forces becomes essential in determining the composition and density of this ghostly layer. The exosphere responds to changes in the solar wind, which can fluctuate in intensity and speed, further influencing particle loss rates. Mercury's lack of a substantial magnetic field allows the solar wind to directly interact with its surface, causing sputtering effects that release atoms into the exosphere. This continuous cycle of loss and replenishment ensures that while the exosphere may be ephemeral, it remains an intriguing subject of study. Understanding these delicate balances helps illuminate the broader dynamics of other celestial bodies with similar conditions, enhancing knowledge of atmospheric behavior in the universe. Exospheres play a pivotal role in the weathering processes of planetary surfaces, particularly in environments where atmospheres are tenuous. The interaction between charged particles from solar winds and the surfaces of these bodies leads to a gradual alteration of their materials. On Mercury, the exosphere, though exceptionally thin, acts as a barrier of sorts, mediating this interaction. Solar radiation and energetic particles collide with the surface, causing a range of chemical reactions. This environment can lead to the formation of regolith, a layer of loose, fragmented material, which gradually reshapes the landscape. The lack of significant atmospheric protection means that such surfaces are subjected to relentless bombardment, resulting in erosion and other physical changes over time. The influence of the exosphere extends to the retention of solar particles, which, while minimal, contributes to the chemical diversity observed in surface materials. Elements such as sodium and potassium are abundant within this region, and their interactions with incoming solar radiation induce unique spectral signatures. These processes yield insights not only into Mercury's geological history, but also into the atmospheric conditions of similar bodies in the solar system. By studying such weathering phenomena, scientists can better understand the long-term evolution of planetary surfaces and their capacity to support life under various environmental conditions. The Mercury dynamics of Mercury's exosphere reveal notable temporal variability, particularly influenced by the planet's eccentric orbit and axial tilt. As the seasons progress, the exosphere undergoes significant alterations in composition and density. This region, though tenuous, experiences fluctuations in the presence of sodium, potassium, and even water vapor, responding to solar radiation and thermal conditions. During perihelion, when Mercury is closest to the Sun, the intense solar energy invigorates the exosphere, elevating the escape rates of lighter elements. The increased solar-wind interaction contributes to a pronounced enhancement in atmospheric density. Conversely, as the planet moves towards aphelion, these gases gradually dissipate, leading to a more sparse and less dynamic exosphere. Temperature variations across Mercury's surface also play a critical role. Daytime temperatures can soar to approximately 400 degrees Celsius, while nighttime plummets to around -200 degrees Celsius. These extremes facilitate the sublimation of surface materials, adding complexity to the exospheric makeup. Seasonal changes affect not only the elemental constituents, but also the spatial distribution of the exosphere, creating regions of varying intensity and concentrations. The relationship between solar activity and Mercury's exosphere highlights the delicate balance of cosmic influences, underscoring how even the most inhospitable environments can exhibit measurable atmospheric phenomena. Understanding these seasonal shifts offers insights into the processes governing exospheric dynamics. Ground-based observations have long provided a window into Mercury's elusive atmosphere, utilizing powerful telescopes equipped with specialized instruments. Researchers can analyze the planet's exosphere from vast distances. This region, characterized by its tenuous gases, is particularly challenging to study due to its proximity to the Sun and the planet's swift orbital speed. Techniques such as spectrography enable scientists to dissect the light reflected from Mercury's surface, revealing the composition of the exosphere. Atomic sodium and potassium, for instance, have been detected, hinting at the processes that supply these elements. The presence of these particular atoms indicates that solar radiation plays a significant role in the exosphere's formation and maintenance. Observations during specific times, such as the planet's greatest elongation, allow for better visibility and data collection. These conditions yield critical information about the exosphere's density and temperature fluctuations. Findings consistently show that it is not only dynamic but also influenced by solar winds, which contribute to variations in its structure. Ground-based studies have also identified transient phenomena, such as the rapid loss of atmospheric particles during solar events. These insights enhance the understanding of Mercury's atmosphere as a complex, evolving feature. Contrary to the expectation that such a small body would lack substantial gaseous layers, the role of ultraviolet spectroscopy in analyzing Mercury's atmosphere reveals profound details about its composition and dynamics. This method allows scientists to measure the light emitted or absorbed by atmospheric constituents, providing a window into the elemental makeup of this planet's tenuous exosphere. It captures the faint glimmer of particles, highlighting the presence of sodium and potassium, which contribute to the distinct spectral signatures of this region. These spectral observations indicate that the exosphere is not merely a static shell, but a fluid environment that reacts to solar wind and radiation. The interaction between solar particles and the surface leads to the ejection of atoms, which are then detected through ultraviolet emissions. Variations in intensity and composition lend insight into the ongoing processes that shape this atmosphere. Mercury's proximity to the Sun enhances the influence of solar radiation. Ultraviolet spectroscopy illustrates how solar activity alters the density and distribution of atmospheric constituents. Observations during heightened solar activity show fluctuations in the abundance of certain elements, underscoring a complex relationship between solar dynamics and atmospheric responses. The precision of this analytical technique allows researchers to refine models predicting atmospheric behavior and evolution. Understanding these interactions not only sheds light on Mercury, but also informs broader questions regarding planetary atmospheres in extreme environments throughout the solar system. The influence of solar cycles on Mercury's exosphere reveals the dynamic interplay between solar activity and atmospheric behavior. During periods of heightened solar output, the intensity of radiation and solar wind increases significantly. This influx energizes the tenuous exosphere, leading to a rise in particle density. These fluctuations can create prominent changes in the composition and structure of the atmosphere, illustrating how even the most minimal air can respond vigorously to external forces. The magnetic field, though weak, plays a crucial role in these interactions. It modifies the pathways of charged particles and influences their collisions with the surface. This can result in the release of additional materials into the exosphere, further enriching its composition. The rapid transition from solar storms to calmer conditions can also lead to the temporary retention of certain elements, contributing to the fragile balance that defines Mercury's atmospheric presence. Variations in temperature due to solar cycles also impact the exosphere's behavior. As the temperature rises, lighter elements may escape more readily into space, while cooler periods can allow for the potential accumulation of volatiles. This cyclical nature reinforces the concept that Mercury, with its almost non-existent atmosphere, remains subject to the whims of the solar environment, continuously shaping its ghostly air layer over time. Research's gravity of Mercury plays a crucial role in the retention of its exosphere, with a gravitational force approximately 38% that of Earth. This factor creates a delicate balance between the retention of particles and their escape into space. Lighter elements, such as hydrogen and helium, find this environment challenging. Despite being present in trace amounts, these constituents are prone to rapid loss, unable to cling to the planet's surface under its weak gravitational pull. In contrast, heavier elements, like sodium and potassium, exhibit a slightly better retention capability. These metals exist within the exosphere in the form of sparse clouds, slowly released from the crust due to solar interactions and micrometeoroid impacts. The dynamic balance between solar radiation pressure and Mercury's gravity determines the composition and density of this tenuous layer. Constant bombardment from solar winds contributes to the erosion of the exosphere, stripping away particles and preventing long-term accumulations. This process results in a transient environment where exospheric materials are in a continual state of flux, influenced by both internal geological activity and external cosmic forces. X-ray emissions play a pivotal role in deciphering Mercury's complex compositions. These high-energy photons, originating primarily from cosmic sources and solar interactions, interact with the surface materials, providing insights into their elemental makeup, detected by specialized instruments aboard spacecraft. X-rays reveal the presence of elements such as magnesium, silicon, and iron, highlighting the planet's geochemical characteristics. This region, with its thin exosphere, allows for the indirect analysis of these emissions. When solar X-rays strike the surface, They eject secondary X-rays that carry specific signatures unique to the elemental constituents. By measuring the intensity and energy of these emissions, scientists can infer the abundance and distribution of various materials scattered across the planet. The data gathered from these emissions also contribute to understanding the geological history of Mercury. Variations in elemental composition can indicate past volcanic activity or the effects of space weathering on the surface. Such insights offer clues to the processes that shaped this planet, providing context for its evolution. The interplay between X-ray emissions and surface materials continues to deepen our understanding of Mercury. Each observation adds another layer of knowledge, revealing the hidden complexities of a planet that, despite its proximity to the Sun, harbors secrets that challenge conventional notions of planetary atmospheres. Erosion plays a pivotal role in shaping the surface of Mercury, influencing both its geology and its tenuous exosphere. This region is marked by an array of craters and basins, relics of ancient impacts that have weathered over billions of years. The lack of substantial atmosphere allows solar winds and micrometeorite impacts to continuously reshape the terrain, gradually eroding its features. The surface material, consisting primarily of silicate minerals and metallic elements, releases small quantities of gas and dust into the exosphere when disturbed. This process contributes to an ever-evolving cycle where particles are both lost to space and replenished through subsequent impacts. The exosphere remains extraordinarily thin, composed largely of sodium, calcium, and magnesium, which are products of this surface erosion. Radiation from the Sun interacts with these elements, creating a dynamic environment where particles are constantly being ionized and expelled. The weak gravitational pull of Mercury ensures that these particles can escape the planet's grasp, leading to a continuous loss of mass. In this context, the interplay between erosion and the exosphere highlights the fragility of Mercury's atmospheric state. Each erosion event not only alters the landscape, but also influences the delicate balance of materials that define its enigmatic presence in the solar system. The weak magnetic field surrounding Mercury contributes significantly to its exospheric dynamics. With limited protection from solar wind and cosmic radiation, this region experiences constant bombardment, resulting in the continuous stripping of particles. The tenuous atmosphere it possesses is primarily composed of oxygen, sodium, hydrogen, helium, and potassium, each element subtly influenced by this fragile magnetic envelope. Anathermanis interactions with the solar wind further complicate these dynamics. Charged particles collide with the exosphere, energizing atoms and leading to the creation of transient phenomena such as bright auroras. This activity occurs predominantly near the poles, where field lines converge, allowing for localized enhancements in particle density. The result is a temporary yet vivid manifestation of atmospheric interaction in an otherwise barren landscape. Proportion isogfratiaphorapidixia Oldham goes rapid changes. Variations in solar activity can lead to significant fluctuations in particle concentration. During solar storms, the influx of energetic particles can momentarily increase as atmospheric density, while calmer periods allow for the gradual loss of material back into space. This constant cycle of gain and loss creates a dynamic equilibrium, shaping the exosphere's structure. Understanding these processes is essential for comprehending Mercury's unique characteristics and its role within the broader context of terrestrial planet evolution in the solar system. Solar flares exert a profound influence on Mercury's delicate exosphere, a phenomenon that underscores the planet's atmospheric fragility. When these intense bursts of radiation and charged particles erupt from the Sun, they interact with the sparse molecules that make up this ghostly layer. The energy emitted during a solar flare can strip away ionized particles, significantly altering its composition and density. This interaction leads to a dynamic state where the exosphere responds almost immediately to solar activity. During periods of heightened solar flare activity, the influx of energetic particles increases, causing fluctuations in the exosphere's structure. The redistribution of these particles can result in temporary enhancements of atmospheric density, albeit fleeting. The effects are most notable on the day side of Mercury, where the direct exposure to solar radiation amplifies the impact. Nadar Comestin hounds in Vosmedzapruthastem, and the planet rotates. The exosphere does not remain static. It constantly evolves, influenced by both solar wind and the planet's weak gravitational pull. This dance of forces creates a transient environment that can rapidly change. The interplay between solar flares and the exosphere provides insight into broader astrophysical processes, including how celestial bodies interact with their parent stars. Understanding these interactions remains crucial for deciphering the complexities of Mercury's atmosphere and its evolution within the solar system. Theoretical models of exospheric escape mechanisms provide insight into how this planet maintains its tenuous atmosphere. Research indicates that particles from the surface, primarily sodium and magnesium, may reach the exosphere through thermal processes or impact events. The extremely high temperatures experienced during the day lead to rapid evaporation, allowing these atoms to ascend into the thin layer of gas surrounding Mercury. Once particles are in the exosphere, their subsequent fate is dictated by a complex interplay of solar radiation and magnetic forces. Ultraviolet light from the Sun ionizes the atoms, imparting energy that can cause them to exceed the planet's gravitational pull. This process of photoionization results in a gradual loss of atmospheric material, as lighter elements escape more readily than heavier ones. Collisions between exospheric atoms also play a significant role in determining the distribution and density of this ghostly envelope. These interactions can lead to the formation of transient clusters, which may influence the overall stability of the atmosphere. The models also suggest that variations in solar activity can significantly impact this escape mechanism. Periods of heightened solar wind may enhance the removal of particles, altering the balance of elements present in this region. The delicate equilibrium between these processes is key to understanding the longevity of Mercury's exosphere. The presence of hydrogen and helium within this tenuous exosphere offers intriguing insights into its formation. Originating from the solar wind, these light elements are continuously supplied to the planet's surface. Solar winds, composed primarily of protons and electrons, collide with Mercury, releasing atoms that become trapped in its weak gravitational field. Helium, particularly, exhibits a fascinating behavior. This element, while abundant in the universe, is rare on terrestrial bodies. It is produced through the nuclear fusion processes within stars and is subsequently ejected into space. As Mercury lacks a significant atmosphere to retain this gas, its presence becomes ephemeral, fluctuating with the solar activity cycle. Hydrogen follows a similar fate, often originating from the decomposition of water molecules in the solar system or direct interaction with solar particles. As a result, its concentration within the exosphere varies, dependent on the balance between solar influx and atmospheric escape. These elements not only reflect the interactions between Mercury and its environment, but also shed light on the planet's geological history. The transient nature of hydrogen and helium suggests a dynamic relationship with the solar wind, encapsulating a planet that, despite its harsh conditions, harbors secrets about the formation of terrestrial bodies. Understanding these dynamics helps clarify the processes at play in this region. The role of dust and debris in Mercury's exosphere is pivotal to its atmospheric composition. Micrometeorite impacts constantly bombard the planet's surface, dislodging tiny particles that contribute to the thin layer of gases surrounding it. This ongoing process introduces a continual influx of elements, primarily sodium, potassium, and magnesium, which are released into the exosphere. These particles form a transient veil, influenced by solar activity and the planet's unique gravitational dynamics. Exosphere plays an essential role, stripping away lighter components from the surface and facilitating the elevation of these particles into the exosphere. This interaction results in a delicate balance, wherein particles are both introduced and lost at a consistent rate. Dust from cometary bodies also adds to the mix, providing additional material that may linger in this tenuous atmosphere. Observations reveal that dust particles can temporarily linger in a suspended state, caught in the gravitational pull of Mercury's weak field. Their presence affects the chemical reactions that occur within the exosphere, altering the ratios of various elements. Consequently, this region is not merely a static environment, but one that is actively shaped by external forces, which ensures a continuous renewal of its gaseous constituents. Such dynamics underscore the complexity of Mercury's atmospheric phenomena, illuminating its remarkable resilience despite the harsh conditions. The contrast between Mercury's exosphere and Titan's dense atmosphere reveals a striking study of extremes. While the former exists as a thin veneer, barely clinging to the surface, Titan boasts a robust and layered atmosphere composed primarily of nitrogen. This region envelops the Moon in a thick haze, facilitating organic chemistry and a unique hydrocarbon cycle that is absent on Mercury. The surface pressure on Titan is more than 1.5 times that of Earth, leading to the presence of stable liquid methane and ethane lakes, a stark difference from the volatile conditions surrounding Mercury. On Titan, atmospheric processes are driven by a complex interplay of temperature and pressure, fostering clouds and precipitation in a manner reminiscent of Earth's weather systems. The low temperatures on Titan, averaging around 190 degrees Kelvin, allow for these unique phenomena to occur, contrasting sharply with the extreme heat experienced on Mercury, where daytime temperatures can exceed 700 degrees Kelvin. But these divergent atmospheric conditions highlight the influence of gravitational forces and distance from the Sun. Titan's substantial mass enables it to retain gases, while Mercury's low gravity fails to hold onto any significant atmosphere. The study of these celestial bodies contributes to the broader understanding of planetary atmospheres and the mechanisms that govern their formation and evolution across the solar system. The Mercury plays a crucial role in shaping its exosphere. This planet, with a rotation period of approximately 58 Earth days, experiences unique thermal conditions. Daytime temperatures can soar to around 430 degrees Celsius, while nighttime temperatures plummet to -170 degrees Celsius. Such extreme temperature fluctuations create a dynamic environment for the sparse particles comprising the exosphere. Solar radiation serves as the primary driver of exospheric behavior. During the long days, intense sunlight bombards the surface, causing the release of atoms and molecules, primarily sodium and potassium. These elements, along with trace amounts of oxygen and hydrogen, are gently propelled into the exosphere. The planet's weak gravitational pull allows these particles to escape into space, resulting in a transient and constantly evolving atmosphere. The slow rotation also means that the planet is exposed to solar wind for extended periods. This interaction contributes to the continuous replenishment and alteration of the exosphere. As the solar wind collides with the exospheric particles, they are ionized, creating a tenuous layer of charged particles that can influence local magnetic fields. Understanding the interplay between rotation and exospheric dynamics emphasizes the delicate balance that defines Mercury's atmosphere, a fascinating subject for ongoing scientific inquiry. Computer simulations have become indispensable tools in modeling Mercury's ghostly exosphere. These advanced programs recreate the complex interactions between solar radiation, magnetic fields, and the planet's surface by incorporating real-time data from spacecraft observations. Researchers can refine their models, honing in on the minute details that characterize this enigmatic atmosphere. As simulations allow scientists to visualize how exospheric particles are generated and lost over time, providing insights into the processes governing their behavior. The intricate dance of solar particles, gravitational forces, and thermal dynamics can be examined in ways that direct observation alone cannot achieve. These models illustrate how fluctuations in solar activity can lead to significant variations in exospheric density. Through this computational lens, it becomes apparent that even the slightest changes in solar wind can result in profound shifts in the exosphere's composition. The simulations also reveal potential pathways for the recycling of materials, hinting at how elements may interact with the surface. Researchers are continuously testing their models against empirical data, ensuring accuracy and reliability. This iterative process not only enhances understanding of Mercury's atmosphere, but also contributes to broader knowledge of planetary atmospheres in general. By unraveling the complexities of this unique environment, scientists edge closer to comprehending the fundamental nature of exospheres across the solar system. International collaborations have become essential in the quest to understand Mercury's ghostly exosphere. Various space agencies, such as NASA and the European Space Agency, have pooled resources and expertise to study this planet. These partnerships enable the sharing of sophisticated instruments and innovative technologies, which enhance the quality of data collected during missions. Joint missions, like the Messenger spacecraft, have illuminated many aspects of Mercury's surface and atmosphere. Data gleaned from these explorations has revealed the presence of sodium and potassium in the exosphere, contributing to the understanding of how solar wind interacts with the planet's surface. Each finding underscores the importance of collaborative efforts as multiple scientific perspectives refine the interpretation of these complex interactions. Research initiatives often involve scientists from various disciplines, from geology to atmospheric physics. This cross-pollination of ideas leads to an enriched understanding of the processes shaping Mercury's environment. Such work highlights the global commitment to unraveling the mysteries of our solar system, emphasizing the interconnectedness of the scientific community. Publications resulting from these collaborations frequently serve as a foundation for future research, ensuring that knowledge continues to evolve. The cumulative effort reflects not only a pursuit of knowledge, but also a shared human endeavor to explore the cosmos, fostering connections beyond geographical boundaries. Future missions planned for Mercury aim to unravel the mysteries of its enigmatic atmosphere and surface. This region, characterized by extreme temperatures and proximity to the Sun, poses unique challenges for exploration. Upcoming spacecraft are designed to study its exosphere, providing insight into how such a thin atmosphere can exist on a planet with minimal gravitational retention. The data collected will shed light on the processes that allow solar wind to interact with the surface, leading to the creation of transient atmospheric particles. This investigation will enhance understanding of elemental composition and the mechanisms of atmospheric loss. It may also reveal the history of Mercury's development, including the impact of solar activity over billions of years. Scientists anticipate that these missions will also explore the polar regions where ice deposits may exist in permanently shadowed craters. Such discoveries could inform theories regarding the retention of volatile compounds in extreme environments. The technology used in these missions is advanced, incorporating improved imaging and spectrometry to analyze surface materials in real time. As humanity continues to push the boundaries of explorations, the knowledge gained from Mercury could have implications far beyond its orbit, influencing our understanding of planetary formation and evolution throughout the solar system. The relationship between the surface composition of Mercury and its exosphere reveals intricate processes at work in this harsh environment. The planet's surface is predominantly composed of silicate rocks and metals, with vast plains and large impact craters shaped by centuries of cosmic bombardment. This rocky terrain contributes essential elements to the thin atmosphere that delicately surrounds it. Elements such as sodium, potassium, and magnesium, emitted from the surface, play crucial roles in forming the exosphere. Solar radiation and the constant bombardment of micrometeorites create a dynamic cycle, causing particles to be ejected into the tenuous atmosphere. It remains an ongoing exchange, with solar wind stripping away volatiles, further influencing the composition of this ephemeral layer. Temperature fluctuations on Mercury are extreme and ranging from approximately -200 degrees Celsius at night to over 400 degrees Celsius during the day. These conditions allow for rapid changes in the behavior of the exosphere. The limited gravitational pull struggles to retain gaseous particles, resulting in a transient and ever-shifting environment. Investigations of this relationship have shown how the exosphere acts as both a reflection of and a response to the surface's geology. Understanding these interactions offers deeper insights into the planet's history and its capacity for maintaining such a fragile atmospheric presence. Observations during transits reveal intriguing details about Mercury's exosphere. This thin layer, comprised primarily of oxygen, sodium, and hydrogen, exhibit variations in density and composition. These fluctuations are influenced by solar activity, as the planet's proximity to the Sun subjects it to intense solar winds and radiation. During specific transits, data collected showcase how the exosphere expands and contracts in response to solar flares. The interplay between solar radiation and magnetic fields contributes to these transient changes. Measurements taken from various spacecraft indicate that the exosphere can rapidly alter, sometimes doubling in thickness when exposed to increased solar energy. In moments of quiet, the exosphere stabilizes, revealing a more consistent compositions. Sodium, in particular, forms a unique feature, creating a faint glow that can be detected from Earth. Such observations provide a glimpse into the delicate balance of forces that maintain this elusive atmospheric layer. The presence of exospheric elements hints at the processes that contribute to their release from the planetary surface. Volcanic activity, impacts, and other geological phenomena are likely contributors, suggesting a dynamic history beneath Mercury's seemingly barren exterior. Each observation during transit adds a piece to the puzzle, gradually enhancing the understanding of this planet that defies expectations regarding atmospheric retention. The Planetary for observation is paramount in the study of this elusive exosphere. Planetary protection protocols play a critical role in ensuring that exploration does not compromise the pristine nature of Mercury or any celestial body. These guidelines aim to prevent biological contamination, thereby preserving the scientific integrity of the environments observed. They dictate the rigorous sterilization of spacecraft before launch, ensuring that no terrestrial microbes interfere with findings or ecosystems. The exploration of Mercury's thin atmosphere requires meticulous attention to detail. The unique characteristics of this region, such as its extreme temperature fluctuations and proximity to the Sun, challenge traditional methods of atmospheric study. Instruments must be designed to withstand intense solar radiation while accurately collecting data on the gaseous constituents that make up the exosphere. In addition, the potential for sample return missions raises questions about the transfer of terrestrial life to Mercury. The implications of such actions extend beyond scientific inquiry, touching upon ethical considerations. Ensuring that the processes involved in exploration do not alter the natural state of this planet is essential for maintaining the integrity of future research. Through careful planning and adherence to planetary protection measures, the pursuit of knowledge regarding Mercury's ghostly exosphere continues, while safeguarding both our planet and those beyond. The challenges of sampling Mercury's exosphere present a complex array of obstacles stemming from its tenuous and transient nature. Characterized by extremely low density, this atmosphere consists primarily of sodium, potassium, and a few other trace elements. Such conditions render conventional sampling methods ineffective, as the particles are often fleeting, scattering into space, rather than remaining bound to the planet. This region experiences drastic temperature fluctuations, with surface temperatures soaring during the day and plummeting at night. These extremes complicate instrumentation, as sensitive devices must endure and operate under conditions that shift from scorching heat to frigid cold. Moreover, the proximity of Mercury to the Sun results in intense solar radiation, which can disrupt the delicate balance of the exosphere and interfere with measurement accuracy. Efforts to capture and analyze the atmospheric particles necessitate innovative approaches, including the deployment of specialized instruments capable of withstanding harsh conditions. Advanced spectrometers and sensors designed for high temperatures and radiation levels are essential for gathering data. Analyzing the gathered samples requires precise calibration and meticulous processing, ensuring that the information reflects the true composition of this elusive atmosphere. Understanding the dynamics of Mercury's exosphere is not just an academic pursuit, it holds implications for broader planetary science, enhancing knowledge of atmospheric formation and evolution across our solar system. Enhancing rays exert a profound influence on Mercury's atmospheric characteristics. These high-energy particles, originating from supernovae and other cosmic phenomena, bombard the planet's surface and interact with its exosphere. The impact of this radiation leads to the ionization of atoms and molecules, contributing to the transient nature of this thin atmosphere. Interactions between cosmic rays and the sparse particles that make up Mercury's exosphere result in the creation of new elements and compounds. This process is critical for understanding how an atmosphere can be sustained in such extreme conditions. The intensity of cosmic radiation varies with solar activity, further complicating the atmospheric composition. Fluctuations in solar winds can enhance or diminish the rate of ionization, demonstrating the delicate balance that governs this region. Mercury's proximity to the Sun amplifies the effects of these cosmic rays. The planet experiences more intense radiation than its more distant counterparts. This dynamic environment influences not only the composition, but also the escape mechanisms of exospheric particles. Some atoms may gain sufficient energy to overcome Mercury's weak gravitational pull, leading to the gradual loss of atmospheric constituents. Research into this phenomenon sheds light on the fundamental processes that govern not only Mercury, but also other celestial bodies with tenuous atmospheres. Understanding these interactions is essential for expanding our comprehension of planetary atmospheres throughout the solar system. Investigations into Mercury's surface reveal a landscape shaped by a complex history of geological activity. This region exhibits remnants of extensive lava flows, suggesting that volcanic processes played a significant role in its evolution. Evidence indicates that these eruptions occurred relatively recently in astronomical terms, hinting at an active interior. The presence of scarps, massive cliffs formed by the contraction of the planet's crust, further supports the theory of ongoing geological processes. As Mercury cooled, it shrank, leading to these dramatic features that stretch for hundreds of kilometers. This phenomenon signals that the planet's interior may still harbor some thermal activity, challenging previous notions that it was a geologically dead world. Seismic activity has also been inferred from the study of surface features, suggesting that it may still experience tectonic movements. The lingering heat from its formation and potential radioactive decay could contribute to this activity, indicating a dynamic interior. Magnetometry studies reveal a magnetic field, which adds another layer of complexity to its geological narrative. The field indicates a partially molten outer core, which could be a source of heat and movement in the planet's crust. These insights collectively reshape the understanding of Mercury, revealing a world that defies expectations, demonstrating that it is not merely a relic of the past, but a planet with a continuously evolving geological story. The interplay of electrodynamic forces plays a crucial role in the behavior of charged particles within Mercury's tenuous exosphere. These forces arise from the planet's magnetic field, which, although weak, acts as a protective barrier against solar wind. Charged particles from the Sun interact with this magnetic field, resulting in complex dynamics that lead to the continuous replenishment of the exosphere. As solar wind streams towards Mercury, it carries a plethora of charged particles, including protons and electrons. Upon encountering this region, some particles become trapped in the planet's magnetic field, spiraling along magnetic lines. This phenomenon leads to the creation of a variable environment where the concentration of ions fluctuates. The influence of electrodynamic forces results in a delicate balance, as these particles are both drawn into and repelled from the planet's surface. The transient nature of the exosphere is further influenced by solar activity. During periods of heightened solar wind intensity, the influx of charged particles can significantly alter the composition and density of this gaseous envelope. This ongoing interaction reflects the planet's dynamic response to external forces, illustrating that it remains an active participant in solar system processes. Understanding these forces provides insight into the intricate relationships between celestial bodies and their environments. Mercury's exosphere serves as a unique case study within the solar system, illustrating the delicate balance between gravitational forces and atmospheric composition. It is the closest planet to the Sun, yet it possesses a remarkably thin atmosphere that is constantly being replenished by solar wind and micrometeorite impacts. This tenuous layer, primarily composed of oxygen, sodium, hydrogen, and helium, occupies a space that challenges traditional concepts of planetary atmospheres. The interactions between solar radiation and Mercury's surface contribute to the dynamic nature of this exosphere. Solar particles bombard the planet, releasing atoms and molecules that escape into its thin atmosphere. This phenomenon offers a glimpse into the evolutionary processes that govern planetary atmospheres, particularly for bodies lacking significant gravitational pull. In comparison to other celestial bodies, Mercury's exosphere is ephemeral, continually subject to the relentless forces at play within the solar system. It highlights the importance of environmental conditions in shaping atmospheric structures, raising questions about the origins and fates of gases surrounding other planets. The dichotomy of its proximity to the Sun and its minimal atmosphere underscores the complex interplay between solar energy and planetary characteristics, yielding significant implications for understanding atmospheric phenomena across the solar system. The relationship between Mercury's exosphere and its magnetosphere is marked by intricate interactions. This planet possesses a weak magnetic field generated by its partially molten iron core. Despite its faintness, this magnetosphere plays a crucial role in influencing the sparse particles that constitute the exosphere. Solar wind, a continuous stream of charged particles emitted by the Sun, encounters this magnetic field, creating a protective barrier that alters the distribution of exospheric components. Particles in the exosphere are primarily sourced from the solar wind, micrometeorite impacts, and the planet's surface. The magnetic field captures some of these particles, causing them to spiral along field lines and occasionally collide with the surface, leading to further release of materials into the exosphere. This dynamic exchange results in a delicate balance where solar activity can enhance the density of the exosphere, while fluctuations in the magnetic field can lead to rapid changes in its composition. Transient in nature, Mercury's exosphere is not a stable environment. The influence of solar radiation can lead to variations in temperature and density, further complicating its structure. Knowledge of this relationship is vital for understanding the planet's atmospheric processes and offers insights into the broader mechanisms governing exospheric systems throughout the solar system and beyond. Transient events within Mercury's exosphere reveal the dynamic nature of this seemingly inhospitable environment. These phenomena, characterized by sudden changes in density and composition, are often linked to solar activity. Fluctuations in solar wind intensity and the impact of coronal mass ejections disturb the tenuous layer surrounding the planet, leading to measurable shifts in its atmospheric conditions. Observations have documented rapid influxes of sodium and magnesium, elements that are not consistently present but appear sporadically. This volatility suggests an ongoing interaction with solar radiation, where particles are ejected and subsequently replenish the exosphere. The lack of a substantial magnetic field allows solar winds to directly influence the exosphere, contributing to these transient events. Instruments aboard spacecraft have successfully captured these occurrences, providing data that enhances understanding of how solar influences shape atmospheric dynamics. The interplay between Mercury's surface and its exosphere underscores an intricate balance, where materials are continuously cycled between the planet and space. These findings have implications for similar bodies in the solar system, where exospheric characteristics may also reflect transient events. The study of Mercury serves as a foundational model for examining atmospheric processes on other celestial bodies, illuminating the universal traits shared by planetary atmospheres influenced by solar interactions. The potential for future discoveries lies within the subtle exospheric anomalies that hint at dynamic processes beyond initial understanding. These fleeting remnants of an atmosphere challenge conventional notions regarding airless worlds. The presence of sodium and potassium, for instance, suggests complex interactions with solar winds and micrometeorite impacts. This region experiences constant bombardment, resulting in the continuous replenishment of its ghostly exosphere. Research indicates that the exosphere undergoes variations influenced by solar activity. During intense solar storms, the influx of charged particles can temporarily enhance the density of certain elements. This fluctuation may offer insights into atmospheric resilience, prompting questions about the mechanisms that sustain even the thinnest layers of air. These phenomena could redefine comprehension of atmospheric longevity across the solar system. Observations from advanced spacecraft, equipped with sensitive instruments, continue to reveal unexpected findings. The detection of atomic species escaping into space opens avenues for understanding atmospheric loss and regeneration processes. The exosphere, while tenuous, serves as a laboratory for studying fundamental physical and chemical interactions. And in turn, these insights may enhance knowledge about other celestial bodies exhibiting similar characteristics. Such explorations not only enrich the narrative of Mercury, but also cultivate a broader understanding of planetary evolution and the diverse environments that exist within our solar system. Long-term monitoring of Mercury's exosphere reveals intricate dynamics that contribute to its unique characteristics. This thin atmosphere, primarily composed of oxygen, sodium, and hydrogen, is influenced by various factors including solar radiation and the planet's extreme temperature fluctuations. Continuous observations allow scientists to track changes in composition and density, providing insights into the interactions between solar wind and the exosphere. Data gathered over extended periods enables the identification of patterns in the exosphere's behavior, particularly during solar events. When solar flares and coronal mass ejections occur, they can temporarily alter the exosphere's structure, leading to variations in particle density and composition. These fluctuations highlight the delicate balance maintained in such a tenuous atmosphere. Monitoring also aids in understanding how exospheric particles escape into space, a process driven by Mercury's weak gravitational field. The rate of this escape has implications for theories surrounding planetary atmospheres and their potential for sustaining life. Insights gained from Mercury's exosphere contribute to a broader comprehension of atmospheric loss processes across the solar system. Additionally, the long-term study of this region enhances knowledge of planetary geological activity. Observations may uncover correlations between exospheric changes and surface phenomena, further illuminating the relationship between atmospheric conditions and planetary evolution. Solar wind variability plays a crucial role in shaping the exosphere of Mercury, influencing its delicate balance. This constant stream of charged particles emanating from the Sun interacts with the planet's weak gravitational field, resulting in the gradual stripping away of atmospheric components. The intensity of these solar winds fluctuates, driven by the solar cycle, with periods of heightened activity leading to increased atmospheric erosion. As the solar wind intensifies, it bombards the exosphere, imparting energy to particles and allowing them to escape more readily into space. This interaction creates a dynamic environment where the composition of the exosphere changes in response to solar variability. The loss of volatile elements, such as sodium and potassium, becomes more pronounced during solar storms, contributing to the planet's atmospheric depletion. Simultaneously, the interaction between solar winds and the magnetic field, albeit weak, creates a protective barrier that can mitigate some atmospheric loss. However, this shielding effect varies, leading to regions where the exosphere is more vulnerable. Such intricate processes underscore the fragility of Mercury's atmospheric structure. Understanding this relationship enhances knowledge of how solar activity influences exospheric dynamics and planetary atmospheres in general, offering insights into the broader mechanisms at play in our solar system. Exospheres serve as a critical bridge in understanding the potential habitability of exoplanets. These outermost layers provide valuable clues about a planet's atmospheric retention capabilities and the influence of its host star. In the search for life beyond Earth, recognizing the characteristics of an exosphere can indicate whether a planet possesses the necessary conditions to support biological processes. Investigating exospheres allows scientists to assess how various factors, such as gravitational pull and solar wind, contribute to atmospheric erosion. Such analyses reveal the potential for gas retention and the likelihood of an atmosphere remaining stable over geological timescales. This stability is essential for sustaining liquid water, a fundamental prerequisite for life as we know it. Data obtained from exoplanets' exospheres can guide targeted exploration efforts, helping to prioritize which celestial bodies warrant closer examination with future telescopic technology. The composition of these atmospheres can also hint at geological and chemical activity, offering further insights into a planet's evolutionary history. Current missions and advancements in observational techniques continue to unveil the complexities of exospheres beyond our solar system. As understanding deepens, the implications extend into realms of astrobiology, planetary formation, and the ongoing quest to determine the prevalence of life in the cosmos. The interplay between exosphere and magnetosphere dynamics reveals the complexities of Mercury's atmospheric behavior. This region, characterized by a tenuous exosphere, interacts intricately with the planet's magnetic field. Charged particles emitted from the solar wind encounter this faint atmosphere, leading to unique phenomena. The magnetic field, although weak compared to other planets, provides a shield against solar radiation, allowing for localized regions where particles can be trapped and channeled. Solar energetic particles collide with the sparse exosphere, resulting in the emission of secondary particles and the release of exospheric constituents into space. This delicate balance influences not only the composition of the exosphere, but also its density and distribution. The rapid rotation of Mercury contributes to these dynamics, generating a complex magnetic environment that varies with solar activity. Observations indicate that during periods of heightened solar wind, the exosphere can expand, allowing for transient changes in density. These fluctuations are crucial for understanding not only Mercury, but also the behavior of other celestial bodies with weak atmospheres. The interplay between the exosphere and magnetosphere provides insights into the processes that govern atmospheric loss, shaping the evolutionary trajectory of planets. This interaction also poses significant questions about the long-term viability of atmospheres in similarly sized celestial bodies across the universe. The exosphere of Mercury plays a crucial role in understanding the processes of planetary formation. This tenuous layer, comprised of atoms and molecules expelled from the surface, offers insights into the conditions that prevail immediately after a planet's inception. It acts as a remnant, preserving the chemical signatures left behind as other elements escape into space. In this region, solar wind and cosmic radiation contribute to the continuous recycling of materials. This ongoing interaction leads to a dynamic balance wherein elements like sodium, potassium, and oxygen are replenished even as they dissipate. The delicate equilibrium observed here reflects the unique conditions of a planet that lacks a substantial gravitational hold. Studying these phenomena aids scientists in piecing together the evolutionary history of terrestrial planets. Insights gleaned from Mercury's exosphere can inform models that predict atmospheric development on planets of similar size and composition. Further examination reveals the influence of solar activity on the exosphere's composition. Variations in radiation intensity directly affect the rate at which materials are ejected from the surface. This relationship underscores the importance of external forces in shaping a planet's atmosphere, or lack thereof, illuminating the complexities surrounding planetary evolution in our solar system and beyond. Understanding these interactions provides a foundation for comprehending the broader cosmic picture. Remote sensing has emerged as a pivotal technique in mapping the elusive exosphere of Mercury. This thin layer of gases, comprised mostly of oxygen, sodium, and hydrogen, presents significant challenges due to its tenuous nature. Instruments aboard spacecraft, such as the Messenger mission, have been crucial in detecting these components. They utilize spectrometers to analyze light reflected off the planet's surface and the gases surrounding it. At the Planetary spectrometers to analyze light reflected off the planet's surface and the gases surrounding it. The data collected provides insights into the composition and density of the exosphere, revealing fluctuations driven by solar activity. Solar wind interacts with the planet's surface, releasing atoms that escape into the exosphere. This interaction is intricately tied to the planet's weak magnetic field, which offers limited protection against solar radiation. Through remote sensing, scientists can observe the variations in the exosphere caused by these solar events, allowing for a detailed understanding of its dynamics. The mapping process involves capturing images and spectra that reveal the distribution of gases and their concentrations at different altitudes. This information is essential for modeling the exosphere's behavior and its response to solar cycles. Case studies of other celestial bodies with weak atmospheres reveal intriguing similarities and contrasts. Mars exhibits a tenuous atmosphere composed mostly of carbon dioxide, with pressures less than 1% of Earth's. Dust storms occasionally engulf the planet, affecting its atmospheric dynamics and leading to temporary fluctuations in temperature and pressure. These events highlight the delicate balance between solar radiation and surface conditions. The Moon, devoid of a substantial atmosphere, presents a unique scenario. Its exosphere is influenced primarily by solar wind and cosmic radiation, leading to the occasional release of sodium and potassium. The absence of a protective atmosphere results in extreme temperature variations, with daytime heat soaring while nights plunge to frigid lows. In contrast, Europa, one of Jupiter's moons, harbors a thin atmosphere primarily composed of oxygen. This layer is vastly different from the dense atmospheres of terrestrial planets, offering a glimpse into the potential for subsurface oceans sustaining life. The weak atmospheric pressure plays a pivotal role in surface interactions, facilitating the transfer of energy between the icy crust and the ocean beneath. Wadors Porabao perished against interplay between the icy crust and the ocean beneath. And Ichi-Keisan underscores the complex interplay between solar influences, radiation, and geological processes, shaping the atmospheres of these diverse planetary bodies. This exploration of weak atmospheres deepens understanding of planetary evolution and the conditions necessary for atmospheric retention. The insights gained from studying Mercury's exosphere inform ongoing research in exoplanetary atmospheres. This region serves as a vital reference point, illuminating the delicate balance between gravitational forces and atmospheric stability. Exoplanets, particularly those within habitable zones, may exhibit similar atmospheric characteristics. Understanding how Mercury maintains a tenuous envelope despite its proximity to the Sun provides a framework for examining how other celestial bodies might retain their gases against hostile conditions. Advancements in detection techniques enhance the ability to analyze the composition of exoplanetary atmospheres. Spectroscopic observations reveal the presence of various molecules, allowing scientists to infer conditions that might support life. The lessons learned from Mercury's evolutionary path play a crucial role in interpreting data collected from distant worlds. Factors such as solar wind interaction and magnetic field influence are critical in shaping atmospheric behavior. The implications extend to the search for biosignatures. it becomes increasingly important to discern which atmospheric components can indicate biological activity. This knowledge steers the focus toward identifying exoplanets with atmospheres that could sustain life, utilizing Mercury's profile as a foundation. Continued exploration of weak atmospheres will refine models that predict atmospheric dynamics. The evolving narrative of atmospheric retention across diverse environments fosters a deeper appreciation for the complex interplay of forces shaping planetary systems throughout the cosmos. The contributions of citizen science to Mercury research highlight the collaborative nature of modern scientific inquiry. Enthusiastic individuals, driven by curiosity and a passion for discovery, actively participate in gathering and analyzing data related to this elusive planet. They engage with telescopic observations, contributing invaluable insights that enrich professional studies. This collaboration enhances the understanding of Mercury's unique characteristics, particularly its tenuous exosphere. Data collected by citizen scientists often complements findings from space missions and ground-based observations. Participants utilize various platforms to report their findings, including the monitoring of light curves and atmospheric phenomena. Such initiatives enable a broader exploration of the planet's environment, facilitating the identification of transient events and subtle changes within the exosphere. Hope of citizen science extends to public outreach and education, fostering a sense of community among enthusiasts and professionals alike. This engagement encourages the dissemination of knowledge regarding Mercury's complexities, stimulating interest in planetary science. Through shared efforts, critical questions about atmospheric dynamics and surface interactions are explored. The collective pursuit of understanding Mercury, combined with technological advancements in observational tools, serves to deepen insights into the challenges of atmospheric retention. Such contributions underscore the significance of collaborative efforts in advancing our understanding of planetary atmospheres throughout the solar system. The historical perception of Mercury is steeped in ancient myth and celestial lore. Considered the messenger of the gods by various civilizations, its swift orbit and elusive nature captivated early astronomers. This small planet's unique characteristics led to interpretations that intertwined observation with imagination, giving rise to a myriad of stories and beliefs. Such narratives often emphasized its dual nature, a harbinger of both fortune and misfortune. Reflecting the complexities of its physical attributes, scientific inquiry into Mercury began to take shape with the advent of the telescope. Observations revealed its phases, akin to those of the Moon, challenging the established viewpoints of the time. Over the centuries, advancements in technology allowed for more detailed studies, eventually leading to the Mariner 10 mission in 1974. Which provided unprecedented insights into its surface and environment. The stark, cratered landscape contrasted sharply with the myths, revealing a planet shaped by impacts and extreme thermal conditions. The discovery of the exosphere, an exceedingly thin layer of gases, further complicated its identity, presenting Mercury as a world that defies ordinary classifications. The intersection of myth and science continues to evolve, as researchers delve into the complexities of this enigmatic planet, unraveling its mysteries while acknowledging the stories that have long surrounded it. The significance of public outreach in Mercury studies cannot be overstated. Engaging a wider audience fosters a shared understanding of this planet's unique characteristics and its role within the solar system. It bridges the gap between scientific exploration and public curiosity, creating a foundation for appreciation of this celestial body. Informative events and accessible resources allow enthusiasts and scholars alike to explore the intricacies of Mercury's exosphere, which maintains a tenuous grip on particles and gases despite its proximity to the Sun. Educational initiatives highlight the importance of this planet's extreme temperatures and its unusual orbital patterns. Outreach programs also emphasize Mercury's geological features, revealing the ancient scarred surfaces that tell tales of a violent past. As researchers share their findings through lectures, social media, and interactive exhibits, they ignite interest in planetary science, encouraging the next generation of scientists. Collaboration with local communities and schools cultivates a sense of ownership in the exploration of Mercury. This fosters a deeper connection, allowing individuals to reflect on the implications of space research on Earth. The narratives surrounding this planet gain depth as stories of discovery and innovation inspire curiosity. Collectively, these efforts contribute to a more informed public, promoting a culture of scientific inquiry and exploration that transcends the boundaries of academia. The future of atmospheric sciences promises a significant evolution through the integration of cutting-edge technologies and innovative methodologies. Advanced satellite systems are being developed to monitor atmospheric changes with unprecedented precision. These instruments will provide real-time data, enabling scientists to observe phenomena such as air quality variations and greenhouse gas fluctuations on a global scale. This region of research benefits from artificial intelligence and machine learning, which enhance data analysis and predictive modeling. Algorithms capable of processing vast datasets will identify patterns and correlations that might elude human researchers. Such advancements will facilitate deeper understanding of complex atmospheric processes and improve forecasting accuracy. Innovative techniques, including remote sensing and in-situ measurements, will complement traditional observation methods. These approaches will yield richer insights into the interactions between various atmospheric layers and the influences of human activity. Furthermore, interdisciplinary collaboration will drive progress, incorporating insights from fields such as meteorology, climatology, and environmental science. The deployment of drones equipped with advanced sensing technology will allow for localized studies of atmospheric phenomena, providing granular data that is often lost in broader models. As these technologies converge, the potential to unravel the mysteries of Earth's atmosphere will expand, fostering a comprehensive understanding that is critical for addressing global challenges related to climate change and air quality management. Complex atmospheric science often encounters significant challenges in communication. The intricate nature of phenomena such as weather patterns, climate change, and air quality can lead to misunderstandings. Scientific terminology, while precise and fluid, may alienate the very audiences that need to grasp these concepts for informed decision-making. This disconnect is compounded by the rapid evolution of data acquisition methods, which generate vast amounts of information. On this region of research, conveying the nuances of atmospheric dynamics requires clarity and accessibility. Simplifying complex ideas without sacrificing accuracy is a delicate balance. Visual aids, such as graphs and models, can illuminate trends, but they may not always translate effectively across diverse audiences. Cultural perceptions of science further complicate the dialogue, as differing beliefs and values shape individuals' interpretations of data and its implications. Effective communication strategies must therefore prioritize engagement. Utilizing relatable analogies and real-world examples can foster comprehension. Collaborations between scientists and communicators can bridge the gap, ensuring that essential information reaches policymakers and the public alike. The responsibility lies in crafting narratives that resonate, not only to inform, but also to inspire action. As atmospheric science continues to evolve, so too must the methods employed to share its findings, ensuring that society remains informed and responsive to the challenges ahead. Fordunal Sordevoir Fortuard, your implications of exospheric studies extend far beyond the immediate understanding of individual celestial bodies. This quest for knowledge informs the broader search for life beyond Earth, revealing the intricate relationships between atmosphere, geology, and potential habitability. The thin exosphere of planets like Mercury provides critical insights into how atmospheres can form and evolve in the absence of significant gravitational pull, presenting a unique case study in planetary science. Detecting trace gases within these exospheres often indicates dynamic processes at play. For instance, solar radiation and micrometeorite impacts can contribute to the distribution of elements and compounds, hinting at the potential for habitability under specific conditions. Understanding these interactions becomes essential when assessing other celestial bodies, particularly those in the habitable zones of their respective stars. The search for life hinges on identifying environments that may harbor the necessary conditions for biological processes. This region of study necessitates a comprehensive examination of not just terrestrial planets, but also moons and exoplanets, where subsurface oceans may exist beneath icy crusts. Each discovery raises further questions about the resilience of life and the various forms it may take in environments vastly different from our own. In light of these revelations, the universe emerges as a complex web of potential, inviting continued exploration and inquiry into its many mysteries. The role of Mercury's exosphere in climate change analog studies is profound, offering insights into planetary atmospheres under extreme conditions. This tenuous layer, composed mostly of oxygen, sodium, and other trace gases, provides a unique opportunity to examine the dynamics of atmospheric interaction and escape. The proximity of this planet to the Sun results in intense solar radiation, which contributes to the continuous replenishment of its exosphere. Observations reveal that this thin veil acts as a natural laboratory, allowing scientists to simulate and understand how various planetary bodies may respond to solar activity and temperature fluctuations. The interaction between solar wind and the exosphere illustrates processes that could parallel atmospheric responses on Earth under similar stressors, such as increased solar output or shifts in solar winds. In these studies, Mercury becomes a proxy for understanding potential future scenarios on Earth, where climate change manifests through rising temperatures and altering atmospheric compositions. By examining how its exosphere evolves over time, researchers can better predict the long-term effects of climate change on terrestrial environments. This investigation not only enhances comprehension of planetary atmospheres, but also emphasizes the interconnectedness of celestial bodies and their climates, beckoning further exploration into their enigmatic behaviors and adaptations. The exploration of lifeless worlds raises profound questions about existence and the conditions necessary for life. It provokes contemplation on the nature of habitability and the thresholds that define a world as alive or inert. The study of barren terrains and desolate atmospheres enhances understanding of the universe's diversity, presenting stark contrasts between vibrant, life-sustaining planets and their barren counterparts. These celestial bodies, stripped of life yet rich in geological history, offer insights into processes that shape planetary evolution. The erosion of surfaces exposed to harsh cosmic elements reveals the relentless forces of time and environment. This region, devoid of biological activity, acts as a natural laboratory for examining the physical and chemical dynamics at play. Philosophically, such investigations challenge anthropocentric viewpoints, inviting reflections on our place within the cosmos. The absence of life does not diminish the significance of these worlds. Instead, it highlights the myriad pathways that planetary systems can take. Each lifeless world serves as a reminder of the delicate balance required for life to flourish, prompting inquiries into the conditions that foster existence elsewhere. Studying these unique environments fosters an appreciation for the complexities of planetary systems and the intricate web of interactions that govern their fates. Each observation pushes humanity to ponder the broader implications of life, existence, and the vast unknowns that lie beyond. The significance of understanding Mercury's exosphere extends beyond the planet itself. This thin layer of gas, almost ephemeral, offers crucial insights into planetary formation and atmospheric dynamics. It holds remnants of solar particles that constantly bombard the surface, illuminating the ongoing interactions between celestial bodies and their environments. The tenuous grip on these gases raises questions about how planets with similar characteristics may develop in different conditions. Research into this region unveils the processes that contribute to the loss of atmospheres on smaller bodies. It serves as a reminder of the delicate balance that sustains atmospheres, particularly for celestial bodies lacking sufficient gravity to retain heavier gases. The implications resonate with studies of exoplanets, where the presence or absence of an atmosphere could determine habitability. The intricacies of this ghostly exosphere also shed light on the history of the solar system. Understanding how Mercury has managed to maintain this fragile layer amidst harsh solar influences offers a window into the evolutionary paths of other planets. Observations contribute to a more nuanced comprehension of atmospheric retention and escape, essential for predicting the future of planetary atmospheres. And this way, Mercury's exosphere becomes a focal point for broader scientific inquiries, connecting humanity to the cosmos and reinforcing the importance of ongoing exploration and discovery. Scholarly works on Mercury's atmospheric phenomena provide valuable insights into its unique conditions. Research articles published in journals such as Planetary and Space Science and Icarus delve into the intricacies of its exosphere, offering detailed analyses of data gathered by various missions. The Messenger spacecraft's findings remain pivotal, with its comprehensive mapping of the planet's surface and magnetic field, revealing key interactions between solar wind and the tenuous atmosphere. Books like Mercury, Tokens, Nam the Delusive Planet compile extensive research and highlight the evolution of our understanding over decades. These resources outline how surface temperatures and solar radiation influence the dynamics of Mercury's exosphere, portraying a planet that defies expectations. Vue-Lurstus summarized the latest advancements in our knowledge, integrating findings from ground-based observations and space missions. The interplay between Mercury's geological features and atmospheric phenomena shows how the planet's history continues to shape its current state. Theses and dissertations from graduate students often introduce novel hypotheses about atmospheric processes. These academic contributions foster a deeper understanding of the balance between volatile elements and solar interactions, further enriching the scientific dialogue surrounding Mercury. Establishing connections through this body of research enhances the comprehension of not only Mercury, but also the broader implications for planetary atmospheres across the solar system.